Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Listeners have asked us to provide pointers to some of the resources we talk about on the show. We now have links to books and articles referenced in recent podcasts that are available on our website. We also offer full transcripts. Go to jimruttshow.com. That's jimruttshow.com. Today's guest is Ken Stanley. Ken leads a research team at OpenAI on the challenge of open-endedness. He was previously a professor of computer science at the University of Central Florida, was also a co-founder of Geometric Intelligence, Inc., which was acquired by Uber. Welcome, Ken.
Thank you, Jim. Glad to be back.
Yeah, it's great to have you back. Ken also appeared recently on EP130, wherein we discussed his extremely interesting book, Why Greatness Cannot Be Planned. Not technical, but some big ideas. If you like this episode, you might want to check that one out too. I really enjoyed that book and our conversation. Ken is also one of the leading practitioners and thought leaders, if I dare say so, in the domain of neuroevolution, which is a topic we're going to talk about today. Those people who listen to the podcast know that this is one of my obsessions, neuroevolution. When I retired from business back in 2001 and set up my lab, the very first project I took on was to design a neuroevolutionary system to grow players for the game of Othello. And there was even a New York Times article written about it, something like, Internet CEO does what? Or said some things like, yeah, when I first saw the things actually getting smarter on their own, the hair on the back of my neck stood up. Because it was like, wow, I had been reading for a couple of years about evolutionary algorithms. I'd even slipped off the gecko one year. But this was my first attempt to actually build something. And it worked. Whoa! And it's been my kind of go-to tool. It's kind of, neural evolution, as I like to say, is the weakest of all methods, but can have some traction on almost any problem. So anyway, it's a real honor to talk to Ken Stanley, one of the dudes from the field. So welcome. We're going to talk fairly broadly today, but a recent paper that Ken was co-author on is one of the anchors, I would say, of the conversation. It's from Nature Machine Learning, and it's called Designing Neural Networks Through NeuroEvolution. And Ken was one of four authors. The others are Jeff Clune, Joel Lehman, and Risto Mikulainen. Is that how you pronounce Risto's name?
I'm probably going to do a bad job. I think it's Mikulainen.
I know he taught me how to say it once. We've met a few times. In fact, we had him at the Santa Fe Institute at a workshop on evolutionary computing for 3 days. But yeah, it's a tough one. You either have one too many or one too few syllables.
Well, in grad school, because he was my advisor, everybody just called him Risto. So we didn't even bother to try.
Yeah, and Risto is kind of like the godfather of neuroevolution. It's amazing how many people you track their career back and they start out at the UT lab. You were one of them, right?
Yeah, it was a great place for that.
In fact, my own work, I actually based it on work of two other people there, Brad Fulmer and David Moriarty.
Right. Predecessors for me.
Yeah, they had something called marker-based encoding, which was kind of a simple-minded but remarkably general method of folding a linear genetic algorithm sequence into a neural net that had both arbitrary weights and arbitrary topology, which was kind of fun. So anyway, before we get started, let's talk a little bit about some definitional things. What is neuroevolution kind of at the highest level? And then we'll kind of dig down from there a little bit before we start talking about the current state of play.
Right. So neuroevolution is basically a combination of two fields. One of them is neural networks, which these days everybody calls deep learning. But neural networks, which means artificial neural networks, which are inspired in some loose way from the fact that we have neural networks inside of our head, which we call our brain. And of course, that's been a real focus of excitement in recent years in artificial intelligence in general. And then the other side of neuroevolution is evolutionary computation, which means that you try to write programs that take some inspiration from how organisms evolved over the course of natural evolution, but now try to translate that into an algorithm so that you can actually evolve things inside the computer. And so what neuroevolution is basically trying to evolve these neural networks, or you can think of it as kind of like evolving brains. And in that sense, it's it's a bit inspired by just the idea that brains did evolve. And so it's kind of intriguing when you think about it. I think that's why I initially found it very intriguing. It's intriguing to think that we could actually do something like what happened in nature inside of a computer and evolve, hopefully, increasingly complex brains.
Yeah, it is pretty cool. Now, it is interesting that the field, particularly of neuroevolution, but even neural computing, has always been kind of a bit of a sideline. It found some glory in the 90s and things like machine control, and I know it had a lot of interesting results in robotics, et cetera. But it's never quite kind of gotten the glory that some of these other techniques have, even though it's remarkably general and remarkably powerful if you're willing to dedicate enough computation to it. In fact, one of your colleagues, Jeff Clune, wrote an article, which I couldn't find, goddammit, to get the title, which he basically recommended if you're working in this field, try not to use the word evolution. Any theory on why it's kind of been a quiet space?
Mm-hmm. That's fair. Yeah, that's a fair characterization. Yeah, to explain things like that is complicated because it's a historical question. Like, why did the field develop the way that it did? I think part of what happened over the history of artificial intelligence is that there was a lot of fascination and respect for formalization and the ability to, in effect, prove things. And one of the things about evolution, when you think about evolution, is that it's sort of like contrary to that kind of philosophy. Like it's more kind of fuzzy and fudgy, and you sort of just say, well, let's just throw these ingredients together and hope for the best. And so it feels a little ad hoc, and that word ad hoc is not really something that people want to be associated with. And so it kind of grew up outside the mainstream because of that, like the field of evolutionary computation in general, outside of the mainstream of AI or machine learning. And I think that, there was a certain sub-community of people who just were fascinated, despite all that, by the idea that you could evolve a brain. So it didn't really matter, all of these things. And that was a small community, though, because it was hard to really break into the field if that was how you dedicated your time, just to evolving stuff. And so when you combine evolution with neural networks, it's a little bit, I think, of a curveball in general for the field, because neural networks have become extremely popular, but evolution remains kind of on the outside. And so it takes a little processing for people to decide what their position is on that. But I think the real issue, though, is that it's very important to articulate motivations. Like, why are we doing this? Because I think ultimately why there wasn't more initial interest than there was because there was a failure perhaps to explain or to motivate why would we want to evolve a neural network. Because basically the response would be that there are better things to do that are more principled. Like, you can follow a gradient. They're gradient-based algorithms like backpropagation. And it's principled because we can compute the gradient and then we know which direction to go, rather than what people would say is just random, like flipping around in mutations and just rolling the die and hoping for the best. And the problem is that deserves a response, but it didn't really get a response. So we're sort of left with this assumption that's not really true, that basically neuroevolution is an optimization algorithm which is inferior. And that there's like good optimization algorithms, and there's just these kind of like roll the die type of random stuff. But the real issue is that neuroevolution to me is not really about optimization. Neuroevolution is about how did we get something astronomically complex out of effectively nothing in a completely unguided process. And it's true that it took maybe 1 billion years or something like that, more than 1 billion years. But it's an incredible story. I mean, it's the only way we've ever gotten something like our brain with its 100 trillion connections. And we want to understand, how is this possible? On the face of it, it doesn't sound like it could be possible. There's the gap between like our nearest ancestor with the apes, which is something like 300,000 generations ago, is pretty small. Like 300,000 generations to get to a human brain. That's a pretty strange thing. And so like to understand how that few steps can be involved in such profound changes, that's the kind of thing I think neuroevolution is about. And ultimately understanding how complexity arises from simplicity.
Another of my favorite topics. One of the reasons I got sucked into the area, because it just seemed like, wow, I mean, we have an existence proof, right? We know that high intelligence came from pond scum. right? And it got there via evolution, at least if you're not a believer that somewhere along the line, and then a miracle occurred, which I am not. And so, yeah, why not do some work on seeing if we can duplicate this one existence proof that we have? And then I will just make one little factual adjustment to what you said. You talk about billions of years of evolution. It's in some ways even more amazing because the neuron only arose about 550 million years ago at the latest, right at the time of the Cambrian explosion. Some people argue just before, some people say as part of. So it's a mere 550 million years that we've gone from the simplest responsive neuron to humans. And that's not all that much time.
Yeah, it's remarkable. And I mean, you have to think about it generationally. It's like how many generations have passed, and like it's getting to the point where the number of generations is not out of the possibility of actually running on a computer that many generations. And so yet, I don't think if we did run an algorithm today for that many generations, it would develop a human brain. So in some way, we're missing something. And that's what's intriguing about it. It's like, what is it that we don't know here? Like evolution is a theory that that's kind of well articulated in a biology textbook, but that's different than actually understanding how to implement it. Like to implement it to be able to do something similar on a similar level of grandiosity is like all of life on Earth. We don't know how that's possible, and that to me was probably inspiring initially. That there's some really missing information here. That could be low-hanging fruit, at least some of it, where we might discover some insights that ultimately help us on the road to AI as well, since after all, the evolution led to intelligence.
Very cool. Well, let's do a couple definitional things for our audience before we get started. You mentioned that this field, neuroevolution, is the junction, essentially, of evolutionary computing and neural nets. Maybe if you could start with describing the simplest generally used evolutionary algorithm, the genetic algorithm, which was developed by my dear friend, now passed, and colleague at SFI, John Holland. And so if you could, describe a genetic algorithm in just the simplest basic form, I think that would be useful for the audience to understand what we're talking about later.
Sure. Yeah, and I didn't know you know John Holland, so that's cool.
Oh, yeah. I mean, he was one of my dear friends, great guy.
Wow, really interesting. Yeah, so to try to do justice to the genetic algorithm, it's a kind of very simple attempt to take inspiration from what you see in nature, in evolution. And you can think of it a little bit like an automatic breeding algorithm. It's like if you take a group of things and they are encoded in something that's like DNA. So we would call that a genome, but we're talking about artificial stuff. So in the computer, so you have a genome. So if that's too abstract, maybe you can think about it as the genome is a description, which explains what something is. So maybe it's like a description of a body plan or something like that. Maybe we're trying to evolve robot body plans, let's just say for the sake of example. So we have these little descriptions. Each one's a little bit different. Maybe it's different, slightly different parameterizations. And we could say, like, let's generate 100 of these like randomized descriptions. So they're pretty terrible probably because they're randomized, but because of statistical variation, some are better than others. And so what we're going to do is just like what breeders would do is we're going to pick things based on how good they are or how fit they are, I guess you would say in evolutionary parlance. And so we're going to sort of rank them or score them. And then we're going to say, let's choose some subset of these to be parents. And those parents are going to have children. And we can do this in a computer because we can take those genomes, which are just little descriptions, and we can perturb them or mutate them slightly to get a slightly different description. And of course, we don't know whether it's better or worse because it's a mutation, but sometimes it is better. And so in the next generation, and also with crossover, we can combine two things as well. Like when you think of two parents and a child, so we can have crossover and mutation. And in the next generation, we let those chosen parents have children. They produce these children. Then we can test all of those and see what their fitness is or how well they perform. And so now we have slightly different robot body plans that are in some cases slightly better. And we do the breeding process again. And then we have another generation. And so now we're basically just breeding over generations automatically, in effect. And that's what the genetic algorithm accomplishes. And it's really cool if you think about the fact that if you just run this thing, there's no human intervention, no human in the loop. Eventually, you expect that things are going to improve just on their own, and you'll have something better at the end.
And they usually do. And it's actually interesting when I actually got down to writing my own GA code, and this may go back to why the somewhat disrespect for the field. The actual technology is remarkably simple to write a basic GA. I think it took me 2 hours to get it working, right? It took me probably half an hour to write the algorithm. And then, of course, my fat fingered fumbling and idiot misunderstandings took me another hour and a half to debug. But yeah, I literally had a simple GA running in an hour and a half or 2 hours and adding different kinds of crossover algorithms and different mutation rates and thinking about it as a circular or a linear. And, all those things are actually very easy. And so that may actually be one of the reasons that the lack of respect is too goddamn easy. So at least to do the inner algorithm, but that of course isn't where the magic lies. So on the other side of it, let's talk about neural nets. Talk very briefly about the neural net as a summation and output mechanism, and then maybe a little bit about the current state of the art of backprop gradient descent and stochastic gradient descent.
Yeah, so neural networks are, like I said, at some level kind of inspired by brains and how they work. And this statement is kind of endlessly controversial, unfortunately. So lots of people love to then jump up and say it's nothing like the brain at all. And other people might argue, actually, there are similarities to the brain. But I don't think it really matters. It's just inspired by that at some loose level. It does have appealing computational properties that seem in some ways reminiscent of what brains can do. Nobody, I think, really thinks it's identical to what brains do. We can try to push in that direction, though. But so how it works with a neural network is that you can think of the fundamental unit in a neural network as what we might call a neuron. And so obviously it's not the same as a biological neuron, but we use that nomenclature. And so the neuron is a little computational unit that if it is sufficiently excited, it itself will fire. And it will output something that we would call its activation level. And so the neurons then are connected in a network. And so some neurons can have connections into other neurons. And so if a neuron that's excited has a connection into another neuron downstream, then that excitement can then trigger the neuron that's further downstream. And those connections generally have something called weights. So it basically says, well, how strongly does the signal going along this connection influence the target of the connection? And those weights you can think of as ultimately determining the functionality of the network. So there's all these different connections between all these different neurons. Signal is moving down from the inputs to the outputs. And the inputs you can think of like sensors, like what you hear, what you see. And the outputs are like control signals like movement or something like that, or talking is another kind of output. And then that cascade of activation, which travels from the inputs to the outputs, ultimately determines the behavior. And it's the weights that determine ultimately what that behavior will be. And so weights are sort of what we're looking for when we talk about neural networks. Is like it's like, if do you want this kind of stimulus to cause this kind of response? Well, it depends on whether there's weights between those 2 points and what those weights are. And so what then happens is that if you think of like some big constellation of neurons all connected to each other, how can you make it do anything useful? Of course, just connecting a bunch of things together doesn't make it do anything. You can send activation through that mess, but it's just spaghetti, so it'll just do something arbitrary and random. And so the job of algorithms that try to optimize these networks to make them functional is to find weights that actually do the job that you want them to do. And so finding weights is the problem. And so there are algorithms for doing that, like gradient descent that you just mentioned. And these algorithms, so gradient descent is the algorithm, probably the most popular algorithm, or stochastic gradient descent, which basically is about saying, if I know what I want the output to be, so say I have some examples, I can show it. Like I can say, what is this? Is this a dog or a cat? And then it answers the question with like a dog or cat response. And then I can say, well, was it right or was it wrong? Of course, an initial randomized neural network will be wrong most of the time. But what I can do then is I can say, well, I know what the answer should have been, so I can compute the difference between what it said and what it should have said. And then I can do something called backpropagation, which basically means sending the signal back from that difference. So I've got this like delta, which says what it should have been. I can send it back through the network and compute for every neuron in the network. I can push it or nudge it a little bit more towards what it should have done by altering the weights that go into that neuron. And if we keep on doing that over and over again, iteratively, then we can gradually nudge the neuron towards the kind of behavior we want, all the neurons, so the whole neural network. And we then have the hope that it will eventually be good on what we just showed it, which we call the training set. And the real hope is that it'll generalize to something like we would call a test set, which means that things it hasn't seen when it was trained. And so if you give enough examples of dogs and cats, then if I show it a cat it never saw before, hopefully it's generalized, is what we would say. And hopefully at that point it knows what a cat is. And there's a little bit of magic there, I think, which is interesting, that you've just shown a bunch of examples. You never had to explain anything. You don't know how it internally works. It just automatically, through gradient descent, optimized those weights. And amazingly, you've got a cat detector at the end. And so that's why this is exciting, I think, to a lot of people.
Very well done. So now we get to neural evolution. Instead of using backprop, let's take the core case, we're using evolution to discover weights and topologies sometimes. Let me try to explain it. You can correct me. So we basically have a linear string of numbers, let's say, in some coded form. And because they're a linear string, we can do crossover and mutation on them using the genetic algorithm to find the better ones and have them reproduce with the other better ones. And then we have some form of an interpreter which can interpret those strings and turn them into a neural net, essentially. And then we can run the neural nets, see how they do, and then find the neural nets that do best, and then do our crossover and mutation by one of the various rules, tournament rules, random with weights, etc., method of how we do reproduction. And that combination of having a linear version of the neural net, an interpreter into its network form, then running those forms, grading their performance, and then running evolution back on the original strings is essentially the simple-minded core version of neural evolution. Is that fair enough?
That is fair. So there's a lot of subtleties here, though, when you talk about this, because the real question I think that it raises for people in machine learning is okay, well, you can do that, but why would you want to do that? We have gradient descent. And so ultimately, like this linear thing, which I would call the genome, which has like basically some kind of encoding of the weights. So as an alternative to backpropagation, what we're talking about here is that the weights are now in the genome and we're evolving those genomes. We're basically evolving the weights of the network in the simplest case. And so you'd say, well, why even do that? We can just use gradient descent, and then we can make principled perturbations instead of like just random perturbations, just hoping for the best. It's still can work, of course, because with selection, it's not an entirely random process. That's important actually to recognize for people who think evolution is random. It's definitely not a random process. It's a stochastic process. And so there are non-random elements here, like the selection of the best stuff. I mean, that's obviously not a random event. And so it's not a random process in the end, and you can expect it to do things like optimize. But the question is it as efficient as something like backpropagation, I think, for people in machine learning? But then you have to sort of say, well, maybe though that kind of perspective is missing the real point here. Because evolution isn't out there to be like the best optimization algorithm in the world. I think it's more interesting that evolution is more of a creative algorithm than an optimization algorithm. And so it's saying it discovered all of life on Earth in a single run. And nothing that backprop does is at all reminiscent of that. And so what you can do with evolution is that it is more of a kind of a creative sandbox where you can play with ideas about creativity and also complexity, which is sort of the idea that what if these neural networks are getting bigger and more complex over time, which they did, of course, in real evolution. That's not addressed by gradient descent either. And not to say that we couldn't imagine some fancy things that we do to try to augment networks while we're running gradient descent. That's conceivable, but it would be also something extending it. And evolution is a natural thing to do, to look at increasing complexity, and then to try to understand how you get these kind of divergent processes that produce all kinds of amazing stuff. And now we're moving outside of the gradient kind of view of the world, because often it's hard to say to actually compute a gradient for something like that. It's not necessarily impossible though. So I think there's some convergence now in deep learning, between deep learning and neuroevolution, where people are getting interested in gradients of novelty and things like that move it closer to what evolution does. And the distinction is blurring in some way. So the conceptual underpinnings become more important than the terminology. But nevertheless, at first, there was a clear distinction, I think, where this kind of creative divergent process was far more easy and natural to explore outside of gradient descent. And that's sort of what this kind of more evolutionary metaphor offered. And we certainly used it to discover some interesting principles.
Yeah, very interesting. You mentioned weights. Back in the history of neural evolution, there was quite a bit of exploration of evolving topologies as well. And in fact, in the work I did, I found that fully connected networks were actually not the best way to do it, at least not with the limited computation capability I had. And it turned out I got much faster learning when I evolved topologies as well as weights. Could you talk about that a little bit? Maybe where's the current thinking about whether it's worth evolving topologies in addition to weights?
Yeah, so that has been a historical significant distinction between neuroevolution and gradient-based neural network optimization because it's easy to evolve topologies in neuroevolution because the problem in gradient-based methods is not clear what the gradient of a topology is. But in neuroevolution, you don't need a gradient, so you don't even worry about it. So now you can do almost anything because you can just introduce mutations that change topology. And there were huge proliferation of neuroevolution algorithms that would evolve topologies because there's so many different ways it could be done. It was very creative. It was kind of a Wild West situation though, because there were basically like no principles. It was just like all kinds of crazy ideas. Let's just see what happens. But in any case, it's appealing that it can be so easily done and experimented with because of the fact that there's an intuition that I think is pretty strong that like topology matters, that structure matters. And if we really genuinely want autonomous algorithm independent of humans to discover intelligence, well, that's appealing that like here's an algorithm that can allow it to discover both the appropriate topology and the weights simultaneously. And when I talked about complexity, that folds into that because in some way, what we're really talking about is expanding the brain to become more complex over generations in a way somewhat reminiscent of what we see in nature as brains became more complex as well through our ancestry. And so there's always been some controversy about whether, though that intuition is appealing in principle, whether it actually makes sense in practice. And there have been times in the course of the field of neuroevolution where some people have argued that it doesn't actually matter. Just give me enough neurons and connections and just evolve the weights and everything will work out. And then other times where there was a strong inclination, or at least even evidence saying that actually topology does matter. In the end, I think topology matters. I believe that's true. Like even in the field of deep learning, we see in the modern day that there are clearly some of the most important innovations are innovations in architecture that enable what's being achieved now with neural networks that are very vast today. And so it's clear that architecture is important. Architecture is basically just the same thing as topology. And so neuroevolution algorithms were very good candidates for just exploring topologies without a huge amount of friction or intellectual challenge of how to convert a topology into a gradient.
Yep, it's interesting. And I must say, I've always been a little depressed to the fact that what became deep learning is almost all structured on fully connected networks. It seems to me like a coward's way out just because it's easy, right? It's easy, but computationally grossly more expensive than it needs to be because every time you add a connection, you have, an associated set of work associated with optimizing that connection. So the boys are missing something there. God damn it. The boys and girls. I guess there's some girls involved these days, which is a good thing. As an amateur, kind of just watching from the outside, it seemed to me like they're missing something when all they do is fully connected networks. Where for the audience, think of a series of rows of nodes. Either the nodes at each level could be connected to all the nodes at the next level down, or just some of them, right? And there's no reason that you can't do one or the other. And there's actually much more interesting, complicated, recurrent architectures, which we'll talk about later in the story. So anyway, with that prelim, why don't you tell us about your NEAT architecture and what it does and sort of where it fits in this history of neural evolution?
Sure. Yeah. So around the year 2000, I was in grad school and I was reading all these papers that were evolving neural network topologies, and I had a whole collection of them. I spent a semester reading them, basically in late 1999. And like I said, it was like a Wild West. There were so many. It was a pretty interesting time because there's like anything goes, and there were basically no principles. I sort of thought, and this is, I was like in my 20s and I was kind of like ambitious, and I was thinking, here's what I'm going to do. I'm going to take all these papers that have all these crazy ideas for evolving neural network topologies. I'm just going to read all of them, take notes, and then I'll just combine all the best ideas. And that will be like my dissertation for getting a PhD or something like that. And that was what I was thinking. And I read all these papers over about 4 months. And at the end, I just was dissatisfied. I was like, none of this makes sense. At least to me, I was like, The problem was there were no principles at all. It was all totally ad hoc. And I was like, there's got to be something better. Like, so I came out having a different view than when I came in, where I was like, there's got to be some like more like systematic thing you can do here, like something that just makes sense. And I kind of sat down and tried to figure this out. Like, is there some way? Basically, the main thing that I was trying to think of was, if I had two different topologies, like, is there some principled way to understand what it would mean to combine those two things like that? Because at the time, like, crossover was a big problem in neuroevolution, because if you have like two different topology brains and they're going to have a child, it's like totally unclear how to combine them. And there's no actually known way of matching up graphs of arbitrary topology perfectly. And so I was like just sitting down with a pencil and paper trying to line up graphs and like say, is there some like meaningful way to do this? And I had a series of kind of revelations, I guess, in going through that very quickly, where I saw that there are ways to do it that are principled if it's in an evolutionary context. I guess that's the inspiration for NEAT. Like, in general, if you just have two arbitrary graphs, there's no clear principle for how to combine them. But if you know their history, like you know where they came from, and if you keep track of that history, then you know, like, for example, is this connection from the same history as that connection in this other potential parent? And so you can line them up. And those came to be known as historical markings, or like you can mark the genes to see where they came from. And that became a fundamental part of NEAT. And then so by cracking that problem, I guess you would say addressing the problem, there's still an issue with arbitrary topologies, but it addresses it sufficiently that you can get around it now. The next thing I realized was, oh, this is really good for speciation if you do this. Like, because now not only do I know how things line up, I know how they're related because I have these historical markings. So I can divide them into species like really easily without any like special computational overhead or expensive computational overhead. And so that then allows you to preserve diversity. Like now, like what evolution does, it's like when you get a really cool new idea, like you don't want it to just die out immediately, even if it's not great right away. And speciation accomplishes that. And then because of that preservation of diversity, you can also do increasing complexity. Because one of the problems with increasing complexity is that it involves risk. Like anytime I increase the complexity of a structure, I probably reduce its fitness at first. So I'll basically throw it out if I'm just doing a standard algorithm, like a genetic algorithm. But if I have speciation, then I can protect it in its own niche, where it's going to be competing with like neural networks instead of with everybody. And so it allows complexification to happen. And when I put those ideas together, that became NEAT. So basically these three ideas, which was the historical markings, the protection of innovation through speciation, and then the complexification or increasing complexity. And they really work together well. It's like a really unified kind of elegant system when you put them all together, because they all kind of make each other work or enable each other and ultimately enable complexification, which is what I was really interested in. The thing I really, really wanted to see was increasingly complex brains. I was less interested in optimization. I was more interested in seeing something that would become bigger and bigger and more complex, like what we see in nature. And NEAT sort of enabled that at a relatively small scale. So by small scale, I mean, like we're talking about adding one connection at a time here, not adding millions at a time or something. So there's still a disconnect from like nature, where like nature, we got up to 100 trillion connections in a human brain. That's not going to happen through NEAT because NEAT is adding one connection at a time. Imagine if every second a new generation was spawned in NEAT. 100 trillion seconds would have to pass and the universe would be over before we had a human brain. So it's still not going to get you to like that level of complexity, but still really, at least, go to the year 2000. It's really intriguing and new that suddenly we have an algorithm that's principled for evolving increasingly complex neural networks in species. And so that was NEAT. And it got more publicized around 2002. And so it's kind of getting old now, unfortunately. Still fairly popular, still people using it.
Yeah, I did some research on a number of papers that have been published using NEAT as its tooling, and it's, I don't know, thousands. It's a bunch. It's certainly the most popular tooling in neural evolution that I could find, at least.
Yeah, it really became popular quickly, to my surprise. I mean, I was a student, so I thought I was doing it for myself, actually. I was like, this is just interesting to me. I have no idea if a single person in the world will ever care other than my advisor. But I started getting emails and lots of people contacting me, and people had heard of it. That so shocked me that I never even knew these people. And so it started spreading. I guess it got viral. But I think it's because complexification is just intuitively really compelling, is my belief why it caught on. Like the supposed story, or the headline story supposedly, is because NEAT got the record in the pole balancing benchmark. And so it was like the best for optimizing neural networks in reinforcement learning problems. And so that's sort of what you have to do to get through the publishing bar, is like you have to beat some benchmark. And that it did. And that was also surprising to me, because that wasn't really the motivation that I had. I wasn't really trying to beat some benchmark. But then when it did beat the benchmark, I was kind of surprised and realized it might be a big deal. So this could help get the word out. And there's reasons that it did ultimately. But really, my thought is that I don't think people really care about pole balancing benchmarks. I think people care about like imagination and like thinking about the universe. And the thing about NEAT that I think is appealing is that it creates a metaphor that's kind of plausible about like increasingly complex brains and how they might arise. And that's something you'd like to play with. If you had a toy that allowed you to play with something like that, it sounds really exciting. And so I think people were just attracted to the fact that now there is a toy like that and you can play with it.
Interesting. There's a little bit of a sideline. I didn't really intend to ask this question, but it seems like the natural point to ask it. At that time, around 2000, you read all the papers and you came up with NEAT, and it worked and it got widely adopted, and it won some benchmark awards and all those good things, which help it propagate in academic space, at least, and even to some degree in the practical space. But there's another approach that was floating around at the time. And actually, this was the kind of the core interest of John Holland, at least in his later years, which is, how do things become emergently modular? How do you pop up layers and build building blocks? I forget the name of the technology. It was another technology out of UT that kind of ran at two levels. One where you were evolving building blocks, and the other where you were orchestrating the building blocks. It never seemed to go anywhere. And I know John Holland worked for his, the last 20 years of his life figuring out a principled way to produce emergence of building blocks, and always failed. Did you think about that approach? Oh, and I should just mention the other field that I dabble in, not as a practitioner, but sort of as a follower, has been genetic programming. And it has the same issue. How do you encapsulate code? Because obviously code is really a network. You can collapse it to tree structures. So very, very similar kinds of issues. And they put all kinds of hacks in, like automatically defined functions and things of that ilk. So your mind must have gone and thought of and rejected the idea of emergent modularity or encapsulation.
Yeah, certainly. It's just an obvious, really important question, and very related to evolutionary algorithms and neuroevolution and brains, of course, which have some degree of modularity, which is obviously you have different parts of your brain. You have the cortex or the thalamus or all these kinds. They're kind of divided into modules, roughly. And so how does that happen? And how can we facilitate it and make it more likely to happen? Or we might also ask, do we need to? Like maybe it just emerges and we don't have to worry about it. And so it's true that this is a complex topic, and that I do think that explicit attempts to kind of force things into a modular configuration haven't been extremely compelling. Like they're not that convincing, and what comes out of them isn't that exciting. And so I guess I tend to be more drawn towards like organic explanations, like where you'd say that, well, as a result of some intrinsic property of a system, like that it kind of organically emerges that something's modular, rather than that I explicitly create like a bi-level algorithm where there's like a top level and a bottom level and some hierarchy that I enforce, and then they all try to come together. I think that kind of thing, it's sort of like, it's too artificial to be as sort of genuinely rich and imprecise is like what you see in nature, where it's not like these modules are explicitly divided from each other. Like sometimes the borders are a little fuzzy, and that looks more like an organic type of a process, like a bottom-up kind of a process. And so I guess I sort of veer towards, are there constraints that explain why things like that happen? Like, for example, there's a cost to having a long-distance connection. It's harder to get a long-distance connection for all kinds of reasons, like from, say, one end of your head to another. Most connections are short, and it's pretty clear why, because there's a lot of stuff in the way if you wanted to have a long connection. And so just having a constraint like that actually encourages a degree of modularity, because most structure tends to be local. And then there's like a very small amount of more global types of connectivity, and that will just lead to something that looks modular. And so by putting in something like a connection length constraint, let's say, which I played with things like that later in my career, like with HyperNEAT, you do start to see things that look modular emerge naturally. And Jeff Kloon's also played with stuff like that too. He's published on that. And so that's sort of where I lean towards that kind of approach. And I think that the kind of explicit enforcement hierarchical, rigid hierarchy doesn't seem as promising to me. But yeah, I don't want to completely dismiss it either.
Yeah, it certainly has never worked very well. I mean, John Holland, just never got there, right? That was his holy grail, like, Einstein's attempts to disprove stochasticity and quantum mechanics, right? Mighty smart guy, spent a long time thinking about it, never solved it. So maybe it's non-solvable. So now let's move on. We've talked about the early history, the basics of neural evolution, NEAT, which was for quite a while the standard. But we're now in a brave new world of neural nets, billions of nodes. In fact, I follow the work in, like GPT-3 and one of the open source competitors called GPT-Neo. And, we're talking billions of parameters. Obviously, something like NEAT or the, 2000 vintage other forms of neuroevolution ain't going to cut it in the world of billions of parameters. So maybe you could talk a little bit about this world and where does neuroevolution fit in the giga-sized and eventually bigger than that networks?
Yeah, the world has changed a lot. And the emergence of these billion plus parameter models, it does change the context for thinking about what do we need evolution for. And basically means that we need to be a lot more precise in the motivation for why we would be evolving something. Because if you go 20 years ago, it's like just like there's all kinds of things that we don't know how to do. And backpropagation itself, you could even argue it just gets trapped in local optima. Like we need something different. Maybe evolution is it. Now things look a bit different now that we can actually backpropagate through multi-billion parameter models, and it's working quite well. And so neuroevolution's role is, I think it's more nuanced at this point. In one sense, it still offers an opportunity for architecture search. And so one thing that hasn't changed is that architecture still matters. When we see things like convolutional units, now transformers, ResNets, like these are all structural innovations that were invented by humans, but they are critical and allow the field to advance. And so it's clear that architecture does matter, and there are probably new innovations that haven't been discovered yet. And it is a possibility that evolution is one way that we could get to those future innovations. Although so far it's been humans that the ones that I enumerated are from humans. But it's not out of the question that evolution is on the table for that. But also, that's not the only place where this kind of evolutionary thinking, I think, still has a role. There's also this idea, I think, that some of the most important ideas that come out of neuroevolution and kind of evolutionary algorithm thinking have to do with diversity, because evolutionary thinking is ultimately about populations. And I think that's really where the value going forward, if you talk about like decades going forward, has a lot of staying power, is because the problem is that even if you have gradient descent with something that is extremely powerful and large, you still have an issue with all of your eggs in one basket type of thinking, where a lot of problems, especially in reinforcement learning, which means where you don't know what the answers are for specific inputs, like you just get sometimes reward or what you might call sparse reward. There's a need to actually have a diversity of experience, or to actually make a diversity of attempts to explore in order to understand the world around you so that you can become good at dealing with that world. And this diversity is probably essential to like making sense of such a complex world as the one that we have. And it's the obtaining of experience that is really important in a diverse sense. Like we need to seek out a diverse set of experience. And this is really closely related to evolutionary thinking, where evolution is basically a divergent system, which is about how to actually gather a whole diversity of stepping stones that then you can branch off of in the future, where you don't know which of the stepping stones will be essential, but some probably are. And so I think that there's a convergence there, and the words become a little more fuzzy, because I can have a population-based type of system that's using gradient descent, and it's not as clear whether it should be called evolutionary in the strictest sense anymore. But ultimately, it's drawing on the ideas from neuroevolution from more recent years. And I think that that's going to continue to happen and to proliferate. And so I think that we just need to be a little more, basically a lot more aware of the intersection between what's happening in deep learning and what's happening in neuroevolution. But ultimately, I think they're complementary to each other. And so it's both sides really could gain from being more aware, not just the neuroevolution side.
Very interesting. Yeah, though there have been some papers published in the last 2 or 3 years where neuroevolution seems to be at least as good and in some cases better than gradient descent just on setting weights.
Mm-hmm. I didn't cover that, but that's true that there's even some room for that. I mean, it's an uphill battle there. If it's just battling on the optimization of weights, like it's an uphill battle for evolution because gradient descent does have the advantage of a principle behind it. But nevertheless, it's true that in some cases it's been shown to be competitive. Like there's these evolution strategies that actually can optimize very large networks that have probably similar magnitudes of weights, at least millions, in reinforcement learning problems. And sometimes they do better than the analogous backpropagation-based reinforcement learning algorithms. And so, like one problem though is hardware. I think like that. Like we've really converged on a hardware paradigm that's like decidedly geared towards backpropagation, like the way that we use GPUs and so forth. And evolution is sort of a different paradigm in a way, and so it's not as clear that it's as well served. But if you had the right hardware set up, I think it may become competitive in some strange situation. Like if I had a million parallel CPUs or maybe GPUs, but basically just configured for activation and not optimization. Then it might start to be that basically what you're effectively doing is you're starting to approximate the gradient through just getting so many samples in a generation that you actually can approximate the gradient. But you can do better than approximate the gradient because you understand the entire landscape around you, not just a single direction, which we call the direction towards the optimum. And that actually might be useful for doing things like trying to get diversity, because we can go out in simultaneous multiple directions that we've computed through something like an evolution strategy. And so, yes, I think while it's getting much less attention, it's not completely off the table that evolution has some theoretical opportunity here to do something interesting still, even in just weight space.
Yeah, it is interesting, the coevolution, hardware, software, and approach. I mean, there was this interesting breakthrough where someone realized you could use a simple-minded function, ReLU, as a transfer function in a neural net, and you could implement that very easily on GPUs, right? If you tried to do a sigmoid or something, you don't get anywhere near as much gain as you do with a more simple-minded transfer function. That one insight alone, to my mind, is what sucked the world into this, I argue, over concentration on gradient descent based, fully connected deep neural nets, which have indeed produced miraculous results. But one could also hypothesize a different hardware world, as you sort of allude to, what some people call compute fabric, where there's, a million cores that have kind of hierarchical caches around them, and that just straight CPU type compute becomes very, very cheap. And there's no reason that it can't be about as cheap as GPU if we had the silicon to do it, which we don't. And yet it's a chicken and egg problem because we don't have this, the deep learning guys got the free ride, right? That the GPU was designed for the game. The idea of ReLU turned out to be the magic trick, at least initially. I'm sure they got other transfer functions now, but that was one that let them GPUize gradient descent. And the rest was this very interesting coevolution of hardware, tools, and approach. And should massively parallel compute fabric be developed for probably some other reason, then perhaps general purpose neural evolution for all aspects of the networks might indeed come back into fashion.
Yeah, you're right. There's been a coevolution. It's quite interesting. It's a historical fact that that's the way things happen to develop. And the tightness of that coevolution is like the algorithms improve and then the hardware improves along with the algorithms. It's been very exclusionary. I mean, if you're not in that paradigm, you're in trouble because you can't take advantage of what's happening there. And so, but it's interesting to think about alternate realities. Like one kind of, I think, turning point paper in some ways in reinforcement learning, at least, was this paper from DeepMind about Atari, where they showed that they could use deep reinforcement learning to solve these Atari games. And I think that it got a lot of people inspired. And it was very impressive to some very influential people, like the leaders of Google, for example. But one interesting thing in hindsight is that it turned out that like we found out much later that actually you can reproduce that level of result. The quality results they got there could have been done through evolution. They were later. So you can get competitive results through an evolutionary algorithm, but it just historically happened that it was first done with the deep learning. And so, but what if it had been published first with an evolutionary algorithm? I mean, what would have been the course of history then? The whole world would have been circling around the evolution strategies. Like, I'm not sure, but it's interesting to think about that. Like a lot of this stuff is contingent on like what just happened to happen, what order.
It's trajectory dependent, as my friend Brian Arthur always likes to point out, who, by the way, will be on the show in a couple of weeks, and we're going to be talking about his book on the nature of technology. Let's jump back a little bit to an issue that's always been key in all kinds of evolutionary computing, not just neuroevolution, and that is the maintenance of diversity. I want you to talk about what that is, what it means, and some of the approaches that are being used today. You alluded to some of them, but go into that particular topic, which is absolutely core. I mean, you go to Gecko, at least back in the day when I used to go in the double aughts, and there'd be a zillion different approaches on how to preserve diversity in your GA ecosystem. So tell us what diversity is, why it's important, and how you get it.
Yeah, so diversity is a really deep topic. It's quite profound if you really get into the weeds of it. But on the surface, it's basically just one of the worst things that can happen in evolution is if the diversity drains out of your population. If you think about it, if you've got a population and everybody starts to be the same, which is easy to happen. If you think about like if you're just breeding like kind of without being very smart about it. Eventually, like you find something you really like, and then you just let it have all the children, and then the children look like it, and then you just keep on selecting things that look similar, and you can converge pretty quickly and drain out your diversity. But diversity is the fuel from which you can make new kinds of innovations, and we don't know which particular type of configuration in some diverse set might lead in the future to something really important, and so it's important to some extent to maintain a degree of diversity in a population, if you're in a population-based algorithm, because of that. Because if you drain out that diversity, then you really lose the power of the algorithm. And so in the field, historically, a lot of people worried about the maintenance of diversity for this reason, because of basically trying to prevent premature convergence, and in fact would sometimes advertise it as why it's better than something like gradient descent, because gradient descent can get stuck, at least in theory, because it is all your eggs in one basket, because it's basically one egg. But here we have a population, so we can maintain diversity, so in principle we don't get stuck. But what's interesting, though, is that is really not the deepest thing that's interesting about diversity. That's like a more superficial thing than most people were thinking about for a long time. But I think as we went on, what we realized is that there's something a lot more profound, which is that actually diversification itself is very powerful, even putting aside optimization entirely. Like if you don't even know where you're going, don't care. We're not trying to solve a problem. We're just trying to push towards diversity. And only that alone has powerful implications. And that's what was sort of the basis of the novelty search algorithm that I introduced with Joe Layman. And it's just, that's something that like what we see in nature is that actually, if you think about nature isn't trying to solve any particular long-term problem. Like there's not a long-term goal, like let's make a human. That wasn't the goal. You just have a continual diversification, or what I would call divergence. It keeps on diverging. And because it's divergent, like it's inherently divergent, that's intrinsic to the algorithm, it means that it keeps on inventing more and more amazing things. And so like just pushing for divergence itself is actually very powerful and important for creativity. And so it's beyond just like facilitating optimization or preventing premature convergence. It's about being creative and continually open-endedly inventing forever. I mean, it requires a strong push towards a certain kind of diversity.
Yeah, very cool. In fact, it's later in my topic list, but let's hop to it now since you introduced it and it's so close to the idea of diversity. Why don't you tell us about your novelty search? This is really interesting stuff.
Right. So yeah, novelty search, which is introduced something like 7 or 8 years after NEAT, was a result of some observations that we made of an experiment we ran called PickBreeder, where we were letting people evolve images or breed images on the internet. Basically, it was like a little toy almost that people could go in and see some images and then like choose one to be a parent, and then it would have children, and then they could choose one of those and it could have children, and especially breeding pictures. And we discovered this really weird phenomenon when we did that, which was that we found out that people who discovered really cool pictures or who bred really good pictures, like there was a picture of a skull, for example, or a car or an alien face and different things, that those always came from people who were not trying to discover them. This is like very paradoxical and sounds like something like Zen or something like that. Like we said to achieve your highest goals, you have to be willing to abandon them. It's like you can't do things unless you're not trying to do them. And this was a principle in Pick Breeder, but it revealed kind of, I think, a really deep aspect or explanation for what happened in nature. Like, why is nature so powerful? Finding things like a human brain or the flight of birds or photosynthesis or things like this is because it isn't trying to actually find them. Like, if it was trying to find them, it wouldn't be able to do that. And that's because it's deceptive. Like, the things that lead to intelligence don't look like intelligence. Like, if you think about, like, what is the predecessor, one of our predecessors that leads to humans, it's actually like a flatworm. And a flatworm was related to the discovery of bilateral symmetry. But you can't give an IQ test to a flatworm and say we're making progress towards Einstein. Like, that doesn't make any sense. And so if you were trying to just maximize IQ, you would just discard the flatworm. And so it's actually better to not be worrying about Einstein if you want to get to Einstein. If you're way back in the age of flatworms, you just should be worried about whether you're doing something interesting in its own right, in its own time. And so this is an explanation for why people couldn't find things by looking for them in Pick Breeder. And when I saw this, because it was just a phenomenon that we observed, I was just completely blown away. Like, it was so profound, like that, like when I saw that, like, people don't find things by looking for them. And I spent weeks trying to process that. Like, I was like, what does that actually mean? Because I was thinking, like, I've been taught, like, from more an engineering tradition that, like, one of the most important things you do is you set your goals, you set your objectives before you go out and try to do something. And that's actually the way that we get progress, is that we say, okay, I'm going to build a car. So what do I need? But here, like, it was exactly the opposite. It's like the only way to get to the car is you can't be trying to get to the car. And then you might get to a car or something else, but it would be something really, really interesting also. And so as I tried to process this, I eventually realized that, like, you can make it. It actually makes sense that, like, the best way in a global sense, like an aggregate sense, to get all kinds of interesting things is not to be trying to get any particular thing. And so I thought, well, we could actually formalize that as an algorithm. And Joel and I talked about this a lot. Like, we can make an algorithm that isn't trying to do anything specific intentionally, but rather is just trying to do new stuff all the time. And that was what led to novelty search. And so novelty search was this idea that let's make an algorithm that only tries to evolve novelty and is rewarded for novelty. And the theory was that if we do that, then it will actually invent really cool and powerful things. And what was actually, like, really amazing about it is that in some domains, it was actually better than trying to solve the problem. So, like, usually in evolutionary algorithms, what you're saying is, I give you a fitness reward for how well you do on the problem that I'm trying to solve. Novelty search, we don't care because we don't know what we're trying to solve. We just say, if you did something new, you get a reward. But actually, even if you do it that way, it actually would get you a better solution than if you were rewarding it for solving the problem better, which is totally counterintuitive, but makes sense if you think about this deceptive property where the things that lead to what you want don't necessarily look like what you want, which is a property of, like, all complex problems. So it's a deep lesson about actually solving problems in general, which is sometimes you have to let go of them in order to eventually make progress. And novelty search is sort of a formal embodiment of that philosophy. It isn't the key to everything, by the way, because one thing, I just don't want the audience to think novelty search will solve all our problems. One thing that you have to keep in mind here is that what it's basically saying is there's a trade-off. If you want to do amazing things, you have to give up knowing which amazing thing you're going to do. And so if you have a specific problem in mind and you say, well, I'm just going to run novelty search, it's going to solve every problem, it's going to do something interesting, but it might not actually solve the problem you have in mind. And so we've traded away that control for something very different, which is more like saying, just do interesting stuff in general. But as such, to me, novelty search is less like a solution to something than a philosophical algorithm. Like, it's basically making a point, which I think is really helpful to think about the way that the world really works, and then try to grapple with that rather than, like, the kind of denial of how we wish the world works, which is that we just set an objective and move towards it and everything's going to work out well.
Yeah, if the audience is interested in this idea, the EP130 that we talked about earlier, where Ken appeared to talk about his book, Why Greatness Cannot Be Planned, is essentially about this philosophical perspective of novelty. And I got to say, it opened my head. When I first started reading the book, I said, this sounded like bullshit to me. But by the time I was done, I said, fuck, I've actually learned something important and new. And I think to make it practical, you got to do something else because otherwise you just wander around all the time. But there's something really new here. This is really an important thought. And if you found this idea interesting, go read his book. Well, let's get back now to neural evolution. One area that even in my own little work, I fooled around with this, which was using evolution to evolve evolution. So evolving the hyperparameters of models. You may tell the audience a little bit what in deep learning might a hyperparameter be and how you might use evolution to search the space of hyperparameters.
Yeah. I mean, machine learning algorithms in general, whether they're evolutionary algorithms or deep learning algorithms, they always come with a set of parameters around them. And sadly, for the people in the field, the parameters matter a lot for whether something's going to work. So it's sometimes thought of as like a dirty secret or something like that, because it's like under the hood, like somebody had to tweak these things very carefully to get this thing to work. And that's the part that the paper doesn't mention. And so it could be something like the learning rate or something like that. In evolution, it's things like the mutation strength, the population size. There's all kinds of parameters in an evolutionary algorithm. There are speciation coefficients that you might need to set. And so, yeah, it occurs to people that, hey, we could actually search for those parameters. Like, why not? Like, so now we're at a meta level. So it's like a meta learning level or a meta evolution level. And it's expensive to do things at a meta level. But now it's, I think people do it. They call it sometimes hyperparameter sweeps or things like that, because it's so important to get the right hyperparameters to see the full potential of what an algorithm can do. And so evolution is, one of the options for that. I mean, because one issue here is that it can be hard to actually compute a gradient of the hyperparameters. And so the evolution doesn't have to worry about that. It can just evolve the hyperparameters. And there are population-based hyperparameter search algorithms that do that, that have been used in practice in the field. And so it's another potential opportunity for evolution. And by the way, it also points to the fact that, when we talk about applications of evolution and things like novelty search, it's also not only about neural networks. So when we talk about hyperparameter optimization, that's one example, but there are lots of potentially interesting things here that aren't neural that we can do also with these kinds of techniques.
Very cool. Well, let's go move on to the next topic, which is seems to be at the cutting edge of some of your thinking and other people around you. And that's the idea of indirect encoding. In biology, we might call it evo-devo. It's actually the same thing, as it turns out. It's one of the things we kind of talk about sometimes at the Santa Fe Institute. So talk about what indirect encoding is.
So like I mentioned a little bit earlier in the show, I was aware from a very early time after NEAT that NEAT was not going to evolve a human brain, simply because of the magnitude of the human brain, like 100 trillion connections. It's like NEAT basically adds one connection at best over a generation, because there's a mutation that can add a connection. You're not going to get to 100 trillion through that. So then what exactly, what allows us to get to this astronomical magnitude of connectivity? And, the reason that it's possible is because the number of genes in your genome is not equal to the number of connections in your head. In other words, there's a lot fewer genes in the genome than connections in your head.
And that's an important point. This is one of the most staggering empirical facts that's appeared recently, is the number of genes is only 30,000. It's like, what the fuck? I mean, that's a really small number. It's not much more than the number of genes in a fruit fly. And yet somehow, so continue.
So we're talking about massive compression. And so that's by the way, 30,000 is like about the number of genes. And then another way to think about it is that within those 30,000 genes, there's about 3 billion base pairs. 3 billion sounds decent, but we're talking about structures here with trillions and trillions of parts. Just the brain alone with 100 trillion connections, but that's only the brain. Like, you got your whole body on top of that. And so 3 billion is actually quite small compared to that. That's about the size of, I've heard it estimated it's around the size of Microsoft Windows. Can you believe that? Like, that's actually a description of a human being, is about the size of Microsoft Windows. So the compression is absolutely incredible and astronomical. And this is what indirect encoding is about. Like in NEAT, like you do have a gene for every connection. Like if you add a new connection, you add a new gene that describes that connection to the genome, and it gets bigger and bigger. But that is not how it is in nature. You have far, far fewer genes or alleles, or however you want to characterize it. Then you have connections in the brain, let alone cells in your body and so forth. Astronomically different orders of magnitude. And so I knew that this is important. Eventually, like neuroevolution has to be evolving indirect encodings if we want truly brain-sized artifacts to emerge from it. And so it turns out that there's a whole set of reasons that such compression is really powerful. It's not just because it's compressed. Like, that's good that it's small, I mean, for efficiency purposes, but there's other things about it too. Like if you have a compressed representation of something like a brain, what it also means is that in effect what you have is a sort of like a procedure, or you can think of almost like a program for how to build it. It's like a recipe. And so what it means is that it has to capture regularities because there's information reuse. That's a really important part of indirect encoding. Like clearly, if you don't have as many units in the genome as you have in the actual body, then there must be reuse of information in the generation of the body, which means, for example, like the instructions that generated your left arm are largely similar to the instructions that generated your right arm. Now, this is actually advantageous evolutionarily because what it means is that if there's innovations on the left, they'll be reflected on the right because it's the same program mostly. And so, like, in other words, you don't have to discover a hand twice. You don't have an ancestor that had only a left hand. And then luckily there was a mutation where it realized they could be good on the right. Like that would be crazy and very improbable. So the regularities that are overarching in the structure of bodies and brains can be preserved and elaborated in a way that respects them. So like the symmetry that we have, if there's elaborations, it will be elaborated symmetrically. It's true that you can break the symmetry, but it's just that the opportunity to exploit the symmetry is there and is very efficient. Like obviously we're not perfectly symmetric, like the heart on the left side and so forth, but the symmetry is there and we can exploit it. And so that makes it very efficient. So you don't have to rediscover things like legs and arms or hands because the symmetry is there, or like cortical columns, like which are largely structured similarly. There's many of them in your brain and your cortex. And so indirect encoding can encode them effectively in a very small, compact way and just say repeat with perhaps some different parameterization as it moves across the surface of the brain. And so what I started to do was to try to think about, well, what should the indirect encoding be for artificial neural networks? Because what needed an indirect encoding eventually is sort of, I believed even early on, that's what's going to be necessary. So I took an Evo-Devo class, actually. I loved Evo-Devo at that point in time. I was like so into Evo-Devo. And I was in the biology department taking Evo-Devo. And yeah, it's just so fascinating. Like which basically Evo-Devo is like the combination of evolution and development together and how they interact. And I took a similar approach to that I did to like the NeuroEvolution algorithms. I was like, or the topology evolving algorithms. I was just trying to look at like all of the different indirect encodings and also how it works in biology. Like how does indirect encoding work in biology, and try to figure it out. And well, through a long story that we can get into if you want, like eventually it led to the HyperNEAT algorithm, which was like basically the indirectly encoded version of NEAT, which now can evolve very, very large neural network structures.
Perfect setup. Now let's tell us about HyperNEAT and also the idea of the compositional pattern producing networks.
Yeah. So this, I think, is an interesting story because it was similar to when I was looking at all of these topology evolving neuroevolution algorithms, when later I was looking at all these indirect encodings that people had invented like a few years later, and kind of similarly thought, I'll just look at all of them and get the best ideas, even though that didn't work for me the last time. But I was thinking that, there's lots of people had thought about indirect encoding before, because it's obviously like a really inspiring topic. And so people have been thinking about it. And I was reading all these indirect encodings, and I was still kind of optimistic, even after reading all these papers, that there's some way to kind of combine all the good ideas. I actually wrote a paper in 2003. It's called A Taxonomy for Artificial Embryogeny. It was a review paper where I tried to categorize all these ideas in indirect encoding so it was really doing it for myself to make sense of how all of these ideas interrelate with each other, because I was hoping to figure out like what to do, what's the best way to do indirect encoding with NEAT. And then I noticed something totally weird, which was completely unexpected. And it was that like people had started using NEAT to create these little things called, they were genetic art programs, basically. And like what they were doing is they were saying, let's have NEAT evolved neural networks output images and then let people breed them. This was before PickBreeder. They were like little standalone apps that you could run in like the early 2000s. And I was playing with them. I thought they were super fun and interesting. But I started to notice something really weird, which is that the images that I was evolving respected things like symmetry, like when they discovered it. So like, in other words, like it was more like an intuition, but it felt to me like what was happening was sort of intuitively reminiscent of what you saw in nature, or what we saw in nature. That like it would establish regularities like symmetry on some structure like a spaceship. And then it would elaborate it respecting that symmetry as I went forward and continued to evolve the image or breed the image. And I was like, that's what indirect encoding is supposed to do. It was totally weird because like I didn't think of what I was playing with as an indirect encoding. I mean, it was a neural network outputting an image. But I couldn't help but notice, like, this is exactly what I've been aiming for. Like, after all this thinking, like, this is doing it better than anything that I've seen. And it's not even supposed to be doing that. And I suddenly, it made me realize that neural networks actually are really good abstractions of DNA. This is a potentially confusing point because, like, this now is sort of like mixing two different metaphors. Like, a neural network is supposed to be an abstraction of a brain, not an abstraction of DNA. But actually, like, information encoding mechanisms have a lot in common, you know, if you think about it. Like both DNA and brains are some way of encoding information. So it's not necessarily that surprising. But when I realized this, I started to understand what the analogy between a neural network and DNA. That like in this composition of functions, which is what a neural network is. Like when one neuron leads into another, it's basically two functions being composed, like one function taking another function's input and then outputting something. And that inside of this composition of functions, there's actually a flow of information, which is similar to what happens when a body plan is built off of like a strand of DNA. And so recognizing that got me really excited because I thought, well, actually, like the solution to the problem of indirect encoding is just a neural network. Like we already have the technology. It's all been invented. But I realized that if I said a neural network is an indirect encoding, it will lead to endless confusion and controversy, I thought, for decades. Because it's mixing metaphors and it's extremely confused. Like it's like your brain is DNA, and I didn't want to convey that. And I wanted to emphasize that the compositional aspect of it is really the insight that makes this a good metaphor or good abstraction of what DNA does. And that's why I introduced the term a compositional pattern producing network. So now I'm not calling it a neural network. It looks a lot like a neural network. It functions like a neural network. There's some differences. Like it has different activation functions, like a symmetric one to capture symmetry. But in a lot of ways, it's like a neural network, but it's being used instead to like take an input and solve a problem or to output a control. It's being used to input coordinates in space and output structure, which is basically like phenotypic structure or the structure of a brain or the structure of a body. And so that's where CPPNs came from, or the compositional pattern producing networks, which are abbreviated CPPN. And then the next big question was, how do you make that into a NeuroEvolution system? So I've got these CPPNs, which can evolve imagery in 2 dimensions. And now I want to evolve neural networks, not just imagery. And this was a little bit of a puzzle for a while because I really believed that there's some way to do this, but I wasn't sure how to convert an image into a brain. Like it's not that straightforward. Eventually we had a breakthrough where we figured it out. We can go into that if you're interested, but I won't go into the details just for time. And that's what led to HyperNEAT. So we figured out how do you get a CPPN, which is basically outputting a pattern in space to be interpreted as a brain, how to get that pattern interpreted as a brain. And then we can evolve using the CPPN as sort of the DNA, really, really big stuff, because we can have a small CPPN encode a very, very large brain. And so it's like a whole new paradigm where you can try new things now.
And then, to make sure I get this clear in my head, that you can evolve in the space of the small CPPN, which then produces very large networks, and then you can test the fitness of those networks and then do the evolution back in CPPN space.
Exactly. Yeah. So you might actually be effectively doing evolution in a low-dimensional space, which is great computationally and for search. But the network itself that it represents, it could be gigantic. It could be very high-dimensional.
And of course, that's exactly Evo-Devo, right? Which is that we are searching in this relatively small space of 30,000 genes or, a couple billion base pair, and the resultant machine's a shitload bigger, right?
Exactly. Yeah.
And now a key part, actually, there's an amazing conversation on my previous episode with a guy named Dennis Waters in his new book, Behavior and Culture in One Dimension, Sequence, Affordances, and the Evolution of Complexity, which is a book I'd recommend you read, by the way. And one of the key points he makes, because he chooses DNA and written language as 2 systems that have generated huge amounts of complexity. But he points out that in both cases, they had to co-evolve their own machinery to interpret the small encoding to the genotype-phenotype mapping. And of course, that's part of Evo-Devo. And in fact, one of the great mysteries of life is how the hell did we evolve all this very complicated machinery for error correction and near error-free duplication in the DNA, RNA, protein world from a noisy world like an RNA world. What the fuck, right? So what about the machinery? Do you evolve the machinery too, or did you just stipulate some form of machinery that goes from the genotype to the phenotype?
I think the right answer is that it's stipulated in our case, or at least in the case of the HyperNEAT. I mean, in some way, it's a privilege that we can stipulate that. I mean, that's one of the privileges of computation. So we kind of sidestepping some issues that are like unavoidable in nature. Like there's a certain physical constraints in the universe and so forth that make life pretty complicated. And that's like, at least when I think about neuroevolution and machine learning, is like I feel like it's something. It is our prerogative to try to abstract away anything that is just sort of unnecessary in the way that happens to be part of physical reality. It's totally fine. And if we were actually like, neuroscientists or computational biologists, I think we want to be faithful to the way that the world actually works. But I don't see myself as that. I'm just an AI researcher. So I'd rather it's actually more interesting to actually strip away these properties of the world if we don't need them. Now, you could argue, though, that maybe the machinery is important in some level of computation. Maybe it does something useful. It's a valid thing to argue. But I guess at least the appeal of stripping it away is that like there's less machinery to deal with computationally.
And that actually makes sense. When we do know that an awful lot of Ma Nature's workarounds are just because of the laws of physics, right? We can duplicate a string in a genetic algorithm trivially, but Ma Nature probably took 500 million years to figure that one out, right?
Yeah, I mean, this is a fascinating topic, actually. Like the fact that nature has to do these really complicated things because it's in this like kind of physical box that it can't get out of. Like if you think about like the development of an embryo, like from an egg, like it's so compelling. I mean, so fascinating to look at like the stages of the embryo development until it's like a full baby form. And you look at that and you're like, that is an extremely powerful process. But then like something like a CPPN, it doesn't even go through things like that. Like basically all it does is it goes directly to the final form. Like it skips all these developmental steps. And so what I get from that is like the things that sometimes are most compelling in nature are really just artifacts of the fact that this is a very inconvenient computational substrate. And so it can be very distracting because like you think like that is the point, like the computational point of the process is embryogenesis. Like that's the amazing achievement. But actually that's just a workaround for the fact that like the whole way things are set up is totally inconvenient. Like there's a much deeper thing going on than just that, which is basically like this indirect encoding and how information is reused and stuff like that. Like it doesn't have to go through a developmental process in order to get that benefit. But it does in nature because there's no other choice, because this is a physical reality. And so I think that's a sort of stumbling block for thinking algorithmically, is that it's hard to get your mind off these extremely salient things that you see in the physical world that are just like amazing, but actually might not matter as much as they seem to, just because they are so amazing when you look at them.
Yeah, you might call that the art of being an evolutionary computation dude, right? Which is, what is of the essence and what is an artifact of the substrate that we're, sort of modeling against. Now, one of the most interesting things, this can be difficult to communicate clearly to our audience. I have confidence that you can do so. Something I was really kind of my eyebrow went up, which is you discussed how using HyperNEAT, you were able to replicate some of the common tools in, advanced third, fourth generation deep learning, that you were able to literally evolve a convolutional neural network, for instance. Now, if you could explain I know it's going to be difficult. We're at the edge of explainability to our audience, what a convolutional neural network is, kind of the geometric patterning that HyperNEAT does, and how you combine some relatively simple patterning rules to produce complex patterning, and how you throw all that shit together in evolution, and you can end up with some stuff that people spent years developing as humans.
So convolution is one of the insights that I think has driven the field of deep learning forward in recent years. And one of the reasons is because it really made practical being able to optimize these very large high-dimensional structures that we've seen do all these impressive things. And the idea is often, most attributed to Jan LeCun. That's the origin of convolution. And so what is it? And convolution is basically an idea about reuse. And you can see now immediately when I say that's why it's very related to indirect encoding, because indirect encoding is also about reuse. And so convolution is just a particular kind of reuse. And basically what it's saying is that there are certain neurons within like the structure of a brain, or an artificial neural network in this case, that are responsible for looking at some local area and doing a kind of a local computation of that area. And so you can think of it as like a little feature detector. Like it could be looking for, is there a mouth here? Like maybe it's part of something that will detect human faces, but it's the mouth detector. And what's interesting, like you could take this mouth detector concept and you could like spread it across a sheet so that like you could check in all kinds of locations whether there's a mouth. And that's basically what the convolution is. Basically, it's like the reinstantiation of the idea all across this sheet, or dragging it across this sheet. And so you're basically repeating the same concept over and over again, or literally the same structure. Like this is a connectivity structure, a weight structure, which is being repeated over and over throughout the substrate. And because of that, what you can do is you can say, let's have lots of convolutional feature detectors for lots of different types of features all in one big network. And then we can reuse them all over the place for different locations. And that's that's like a explicit reuse. I mean, it really got the same connectivity, but just moved around in the location within the network. And so, of course, it looks immediately like indirect encoding could just discover the idea of convolution. So that's sort of like the kind of interesting underlying point here is like, we already know about convolution. So in some way, we don't really need to rediscover it because it's already there. But like, if you want to just make a point and say, well, could indirect encoding have done that? Like, did we really need LeCun? Like eventually, an indirect encoding would have just invented that on its own. That is actually true. So like, yeah, if you evolve HyperNEAT networks in a situation where convolution is advantageous, and you do a few preliminaries in order for it to be possible for there to be convolution in the system, then it's very likely to discover convolution or something reminiscent or a lot like convolution, and so not surprisingly, it did.
Very cool. And of course, the interesting thing is that there may be lots of other cool techniques that are pattern based that we don't have to wait for the next LeCun for if we turn HyperNEAT loose on these problems.
Exactly, yeah, because that's the intriguing thing about indirect encoding. I mean, like it's a LeCun deserves a lot of credit for like being the first to have this very deep insight that's very important, but it's just one insight about regularity. Right? It's about regularity. It's a regular structure, a repeating structure. It's not the only, I mean, certainly not going to be the only insight about regular structure in brains. I mean, there's going to be others, and they may have very different presentation than just like the repetition of a certain thing locally. But all of those can be captured mathematically, like in an indirect encoding. Like you can describe any kind of regular structure whatsoever. You can describe fractal structures. I mean, there's anything that you could imagine. And so to the extent that anything like that is actually useful from a neural processing point of view, at least theoretically, it's possible that indirect encoding could reveal it.
Are you or other people you're aware of actually now trying to apply indirect encoding to big real world problems?
Let's see. I am not. I just haven't not recently been trying to do that. Although I think it's still really interesting. So that's sad. I just can't do everything. But I wish I was still trying to do that because it still remains interesting and on the table. There may be others though that are. Yeah, I mean there are other people working on indirect encoding still. I still see dissertations coming out about it. So it's eligible. It's out there. It's still, but the challenge is basically the hardware issue where a lot of the hardware support that facilitates doing something like research in indirect encoding is not directly aligned with the current paradigm that really supports deep learning. It makes it more expensive, and that somewhat undermines the motivation because, like, what we're saying is maybe there's an efficient way to find ideas that we wouldn't have otherwise found, but now it becomes inefficient because it's so expensive from a hardware perspective to perform the search. And it's kind of a shame because, like, in principle, this could actually lead to some interesting discoveries.
Is there a modern implementation of HyperNEAT out there? The ones I found were basically hacked into the old neat code base.
Oh, yeah. There are Python HyperNEATs available. And actually, I have a page which I maintain, which maybe you could provide the link later if I send it to you. But
Yeah, send an email to me. We'll put it on the episode page and people can find that code for people who want to play around with it. And the old, I fooled around some with the C# neat, HyperNEAT, and easy enough code, actually. That'd be interesting to look at the Python one.
Yeah, I mean, it was a really good platform. Yeah, it was a great platform. I mean, Colin Green made the most popular one, and just we used it. It was super good. But yeah, more recently, people have created these Python-based neats and HyperNEATs, and I have some links to them from a page that I was maintaining.
We'll do that. So let's ditch one of my favorite topics, which is Baldwinian learning or the evolution of learning. Well, why don't you talk briefly about that one, the evolution of learning itself and learning mechanism?
Well, I think it's a naturally appealing offshoot of just evolving brains is that, well, brains obviously can learn. Like they're dynamic systems or dynamical systems. They are not static in general. And so it's true that like basically like once you a lot of the time in neuroevolution, if you evolve a neural network, like you find a configuration of weights that serves your purposes and can solve a task. And then it's just kind of frozen that way. And then it just solves that task. And that's not really a good analogy with nature, where like when an organism is born, it's going to go through a dynamic process over its lifetime where it's learning. And what's really cool about that is the mechanism of learning itself was evolved. And in that sense, evolution is a meta-learning algorithm, not just a learning algorithm, because it basically created systems that learn, including our own brain. And so if there's a holy grail for neuroevolution, it can't leave that out. I mean, that's like a fundamental part of it. If we're going to evolve brain-like things, those things are going to have to be learning systems themselves. And so that means that neuroevolution has to find the learning algorithm in addition to the structure and weights of the network. Or in another way of saying is that it would find the learning mechanism instead of finding the weights, because the learning mechanism would ultimately determine the weights, and the weights would always be fluctuating because the system is always learning. But you can do that. Why not? Like evolution can encode rules. We call them rules, the rules of learning. And basically they can be called what was called local learning rules, which means like in a particular connection between two neurons, what decides how that weight should change. And there's a lot of history of evolving local learning rules and trying to get what we call plastic neural networks to evolve that change over their lifetime. So that's a whole other fun area to explore.
Yeah, it's an area that current deep learning gradient descent just ain't very good at, right? It's not really appropriate for that architecture.
Yeah, so to learn systems that to learn systems that learn. Well, they actually are. They're getting interested in that in recent years. It's true. Like historically, they weren't, but the whole issue of meta learning is now something that gets a lot of attention. And I did work with when I was at Uber with Thomas McConey, who published a number of papers that I would encourage people to search for Thomas McConey that were very imaginative about using gradient descent to optimize learning rules, which are actually inspired by the neuroevolution work. So I think it's an example of that the cross fertilization of these two things is really the right way to go. It's not so great to think of these as like two competing paradigms, like neuroevolution versus deep learning, but they're very related to each other. There were years of ideas that came out of evolving learning rules that then McConey just transferred over to gradient descent, and that's elegant, I think.
Yeah, do send me those papers. I'd like to read them myself, and we'll post them on the episode page. Last topic. One of my pet peeves about deep learning, when we think about comparing artificial to human neural nets, is that most deep learning is mostly feed forward. There's obviously more exceptions to that. And, we've always had local recurrence, the old Elman networks, and then LSTM, et cetera. But the recurrence is small, right? And in the brain, we know there's vast long-range feedbacks and feed forwards. It's thought that 90% of the neurons in the visual system are actually feedback from considerably higher levels, some of them all the way up to the top. And yet today's neural net architectures tend not to be anything like that. And part of it is no one's figured out how to do gradient descent on wildly recurrent networks. And yet evolution doesn't care, right? You can put neuroevolution to work on the most tangled, crazed, long-range, recurrent, circular network you want, and it'll work just fine. Has there been a bottlenecking, a narrowing of the field of architectural work in neural nets around the obsession with gradient descent that neural evolution might be able to open up much, much wider thinking about long-range feedback, feed forward, resonances, rhythms? We know the brain is substantially driven by rhythms. There's a lot of work about, phase signaling within the brain. Things like that just aren't possible in feed forward networking. You really need fully recurrent networks, long-range recurrent. In fact, probably something like small world recurrent networks to get at, and that maybe evolution is the obvious tool for exploring that kind of space.
Yeah. So, I mean, first, I would have to acknowledge that in very recent years, there's been huge progress in deep learning on training recurrent networks. So they're making progress. But the point still stands that those networks still have a kind of a stereotyped structure, and that NeuroEvolution can really think out of the box in terms of like recurrent structure. And it can offer you something you've never seen before very easily. It is a possibility, I think, that there are exotic recurrent structures that are just not even being complicated that can be quite powerful, but they're very difficult to think of just through human intuition. And so NeuroEvolution is like you say, it's sort of like unconstrained in this way that there's no issue with how the optimization algorithm deals with the recurrent structures. It can do whatever it wants. It can play with all kinds of crazy recurrent structure, total spaghetti if it wants. And it can make it work. And in that sense, there's an opportunity potentially, to discover something. Like if you think about advances like transformer networks recently, which are used, like, for example, inside of GPT, that just shows that like there's room for substantial new ideas in structure and architecture. And to understand that there is a need for recurrence in a sense. I mean, memory is obviously very important. And so, yeah, it's possible that NeuroEvolution could offer something there.
Cool. That's one of my pet peeves about the world has become so channelized to mostly feed forward with minor bits of recurrence when we know the brain ain't that way. So I want to thank Ken Stanley a tremendous amount for a very good deep dive into the history of and the current state of play of neuroevolution. So Ken, it's great to have you.
It was great to be here again. Yeah, always great to be here.
Production services and audio editing by Jared Janes Consulting. Music by Tom Muller at modernspacemusic.com.